joint work with my collaborators at Cornell and Yale University. Now I'm going to describe what oblivious data access means. Consider the typical scenario where you have a client interacting with the server, which is in untrusted domain, and the server is running a key value store. The client offloads sensitive data to the key value store, such as medical records or company IP property. The client encrypts the objects that's storing in the key value store such that nobody can observe the contents of those objects. Now, any adversary that sees this key value store, although it cannot see the contents of the store, it can still see the access distribution for those random objects. The adversary can then correlate this output access distribution to the underlying input distribution that it can have a prior knowledge of. And in this example, it is able to relate that the most popular random object is actually the underlying key A, just by the access distribution. In short, encryption is not enough, and we need to hide access patterns. The term oblivious data access captures this notion of security. So the output distribution should really be independent of the underlying input distribution. Now we are going to see existing oblivious data access techniques. Existing techniques typically introduce a proxy server between the client and the KV store such that the input distribution is flattened and the output distribution is really uniform random. There are two lines of work on these techniques. The first one is ORAM kind, where you have large bandwidth overheads, namely O log n, where n is the number of key value pairs. The adversarial model for ORAM work is active adversary, where adversary can inject its own queries. On the other hand, there is a new line of work called Pancake, which has only constant bandwidth overhead, namely 3x. It works with an honest but curious adversarial model, where the adversary cannot inject its own queries. However, all these systems have one thing in common. They use a centralized stateful proxy. In this work, I'm going to first describe what are the challenges with the centralized stateful proxy. Specifically, it is either insecure or leads to large downtimes, and second, it has scalability bottlenecks. Next, I'm going to walk you through the design of SHORTSTACK, which is a distributed, fault-tolerant, oblivious data access system. Finally, I'll briefly touch upon our security model, which enables formal study of these systems, such as SHORTSTACK. Now, on to the challenges with centralized oblivious data access systems. We'll use Pancake as an example. To that end, let me give a brief overview of Pancake. Pancake is a centralized stateful system which flattens an input distribution to an output distribution. There are three important functionalities for Pancake. First, it creates replicas for the underlying keys. So the key A is most popular. It creates two replicas which are encrypted and look random to an adversary. Similarly, it creates one replica for key B, C, and D, and so forth. Having done this replication, you can see that the output distribution is almost already uniform. However, as a final step to really flatten this distribution, it injects fake accesses to the least popular keys, C and D. And finally, you can see that the output access distribution is uniform random. Finally, it does query execution in order to satisfy the client request. It also temporarily buffers writes to these replicas so that it can propagate asynchronously the new value to all the replicas. Now, I'm going to describe the challenges with such centralized and stateful proxy systems. Besides the obvious challenge of scalability bottleneck, I'm going to show you that there are much more critical challenges. Consider our running example where a client issues a write request for key A with a new value, the green value. The proxy buffers this write or caches this write and then propagates that to one of the replicas. Now, in a failure-prone deployment, this proxy can fail, and you replace it with a new proxy that does not have that state. Now, when a client issues a read request, there is inconsistency across the replicas of key A. So the question is, how do you satisfy this read request? Either you can fetch all the replicas for key A in order to determine what is the latest value by some versioning, and then you can satisfy the client request. However, this leads to security violations because any adversary that observes this access pattern will be able to see that these two random replicas really belong to the underlying key A. We do not want that. In order to get around the security violation, one could imagine fetching all the replicas such that the adversary is not able to see any distribution sensitive information. However, this clearly leads to huge bandwidth overhead and large downtimes for your system. In short, a centralized stateful proxy system will have either security violations or long periods of unavailability, besides the obvious challenges with scalability. Now I'm going to walk you through the design of SHORTSTACK, which is a distributed, fault-tolerant, oblivious data access system. SHORTSTACK, rather than having a centralized proxy, has distributed proxies in order to achieve its properties. The first property is it maintains the oblivious data access guarantee even under failures. We use a fail-stop failure model, and we allow arbitrary failures to happen at arbitrary times, although these failures should, of course, be bounded by some parameter. Second, it guarantees system availability despite failures. And third, it achieves scalability, which means that the throughput is linear in number of physical servers that our design uses by alleviating compute and bandwidth bottlenecks. Lastly, SHORTSTACK has an honest but curious adversarial threat model, which is similar to Pancake. The key insight behind SHORTSTACK is as follows. Obliviousness only requires that the output distribution be independent of the input distribution. Now, the uniform distribution that all the existing techniques achieve is one but not the only way to achieve independence. Here is an example. Suppose you have an input distribution which is flattened into an output distribution, and now one of the proxy server fails. This means the accesses to even a few replicas would just go away. And clearly, this distribution is not uniform. However, this is not really a security problem as long as any other input distribution also gives you the same output distribution. So now I'm going to describe the design principles behind SHORTSTACK. The first design principle really realizes our key insight. It says the partitioning of query execution should be done over replicas in a distributed design. Here, for our example, there are two partitions for the proxy, and they handle different replicas. Even if one replica fails, remember that the replicas are really random objects. So you do not leak any distribution sensitive information, even if some accesses for those replicas go away. The output distribution is still independent of the input distribution. Now, coming on to the second design principle, it concerns itself with the state of the proxy. I'm going to give you an intuition by our running example. So consider the proxy state, which maintains the mapping for key A, B, C, and D and their values. Now, if we were to not partition this state by keys, but say rather by replicas, then you'll have such partitioning. Here you can see that the key A appears in two different partitions. If you do not talk among these partitions, then that would lead to inconsistencies. So you really need expensive synchronization mechanisms. Therefore, we decouple this state functionality into another layer which is really partitioned by keys. So now you can see that the state for key A resides in one single partition, and so on for other keys. Now, coming on to design principle number 3. The query generation should be done over all the keys. In order to see why this is needed, here is an example. Consider that you partition your query generation over these two proxy servers, where the query generation for A and B happens from the first proxy, and query generation from C and D happens to the second proxy. You'll notice something like this, where the distribution inside the first partition is uniform, and the distribution inside the second partition is uniform, but across both the partitions as a whole, the distribution is not uniform. This is non-oblivious access, and we do not want it. So we introduce a new layer where the proxy servers do query generation over all the keys. Each proxy server in that layer will do query generation independently. And the output distribution as a result is uniform across all the keys. We have arrived at the logical design of SHORTSTACK. This logical design has 3 layers. The first layer does query generation. The second layer does maintenance of proxy state. And the third layer does query execution. Now, how do these proxy layers communicate between each other, or how are the requests routed between each other? So the clients randomly route requests to the first layer proxy servers because these proxy servers independently do query generation over all the keys. From the first to the second layer, queries are routed by keys because that's how layer 2 is partitioned. And from layer 2 to layer 3, queries are routed by replicas because layer 3 is partitioned according to replicas. Now, in order to see fault tolerance for short stack, consider this example where you have 3 servers in each layer. We have already seen that failures in the layer 3, which is partitioned by replicas, that does not lead to any security violation. So upon failure, we can simply reroute those requests to the remaining healthy servers in layer 3. Layer 1 and 2, they handle failures through chain replication with enough replication factor. Now, this might leave you with an impression that SHORTSTACK needs so many proxy servers. However, that is not the case. For our example, we only need 3 physical servers. So the first physical server packs these logical components as shown on the screen. The second physical server packs the following components, and the remaining components are packed onto the third physical server. Now, you might notice that for any physical server, even if, say, 2 physical servers fail here, a chain is still alive. So different components from different chains are packed onto the same physical server. For this example, SHORTSTACK only needs 3 physical servers to handle 2 failures. And in general, SHORTSTACK needs only F plus 1 physical servers to handle F failures. Now I'm going to briefly touch upon the security model. We introduce a new security model because the existing models do not capture failures. In our security model, we let the adversary do arbitrary failures at arbitrary times, although these failures have to be bounded by a parameter f. Next, we only require the output distribution to be independent of the input distribution in our security model. More formal definitions, proofs, and theorems can be found in our paper. Now, lastly, I want to talk about evaluation. We implement SHORTSTACK end-to-end and open source this implementation. Crucially, SHORTSTACK requires no modification to the key value store. We run our evaluations on EC2 with Redis as the key value store and the workloads as YCSBA and YCSBC. The main goal of SHORTSTACK evaluation is to see how SHORTSTACK throughput scales linearly with number of physical servers. Here's the result where the red line shows that the throughput with a centralized proxy system, when you have 1 physical server in SHORTSTACK, it is able to achieve the same throughput. When you introduce more physical servers, the throughput scales linearly. So with 2 physical servers, the throughput doubles, triples with 3 physical servers, and so on. We have many more results in the paper. I would encourage you to look at the paper. In conclusion, there are many challenges with a centralized Oblivious data access system. We introduced design of SHORTSTACK, which is a distributed fault-tolerant Oblivious data access system. We also introduced a new model that enables you to study these systems such as SHORTSTACK. More details about our implementation and artifacts can be found on the following link. Thank you. I'm happy to take questions.